Hey, my name is Henry Testa. This is Lab 4, Circuits. So the purpose of this experiment is to predict the behavior of circuits containing resistors in series and parallel, use multimeters to measure the actual values of conventional current and potential differences in the circuit, and examine the behavior of ohmic resistors and capacitors. So for a brief preview of the results, the current found in part 1 of the experiment was 0.01 amperes, the voltage in part 2 was 3 volts, the circuit satisfies loop rule in part 3 of the experiment, and in part 4 of the experiment, RC capacitor discharge length for predicted was 6 seconds and experimental 7.05 seconds. There's one assumption made, which is that the resistance of wires and ammeters is considered to be negligible. So the fundamental principles of this lab includes Kirchhoff's circuit law, which include the node rule and the loop rule, where current flowing into the node equals current flowing out of the node, and the sum of all potential differences in the loop is zero. There's Ohm's law, where V equals IR, capacitance, where C equals Q over V, conservation of energy and charge, equivalent resistance in series, where R series equals the sum of all resistances in the circuit, the concept of batteries, resistors, capacitors, ammeters, and voltmeters, and lastly, linearization for resistor capacitor or RC circuits. Consider a simple series circuit of two 1.5 volt batteries, two resistors, two ammeters, as shown in the diagram below. Predict the currents I1 and I2 that will be measured by two ammeters. So according to node rule, I1 and I2 are equal to each other. So after calculating them, it was found to be 0.0204 amperes for each one. So in part 1 of the experiment, the system was a series circuit consisting of one ammeter, two 1.5 volt batteries, and two resistors. The surroundings were everything else. And for values, the actual current for I1 and I2 were found to be 0.01 amperes, which is different from the predicted current, which was found to be 0.02 amperes. In part 2 of the experiment, it is also a series circuit, but this time the ammeter is replaced with a voltmeter. And this had a value of 3.00 volts. And if I did have an extra multimeter, it would be ammeter, which predicted 0 amperes calculated. And this indicates that the voltmeter has a high resistance and reduces current to a negligible amount. So for part 3 of the experiment, the system is a series circuit with two 1.5 volt batteries and two resistors, and one voltmeter on the side. So the potential differences, when calculating all of them for each part of the circuit, found to be 0 volts, and this satisfies the loop rule, as the round trip potential is equal to 0. And this is a potential difference graph, which shows all the potential differences across the circuit. Lastly, for the fourth part of the experiment, the system is an RC circuit with one ammeter, two 1.5 volt batteries, two resistors, and one light bulb with 30 ohms of resistance. And the surroundings are again everything else. So for observations, the capacitor discharged for 7.05 seconds, and the current flowing through the light bulb gradually decreased, with the bulb growing dimmer. And if there was a higher resistance light bulb, there would be a longer discharge length. If there's a shorter or smaller resistance light bulb, there will be a shorter discharge length. For calculating the slope of a linearization for RC circuits, it would be negative 1 over RC, and this was found to be negative 0.167 seconds. The predicted RC was this R times C, which is 6 seconds, and the experimental RC was found to be 7.05 seconds. So given data for voltage at every second, it is possible to make a graph that effectively represents the data, and it would be inversely proportional to time. So possible errors, there are human, where I could have incorrectly set up the circuits, I could have incorrectly recorded values from ammeters, voltmeters, and stopwatch, and potential calculation errors could have been made throughout the experiment. Discussion. What if you're doing this lab online and use an ideal simulated ammeter instead of a real ammeter? What's different about an online ammeter, and how would it have affected the circuits you hooked it up to? Well, an ideal simulated ammeter would have zero resistance, so the experimental current would have been equal in value to the predicted one. And what if you were doing this lab online and used an idle battery to charge an idle capacitor with no resistance in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? And the model would predict the capacitor to charge instantly, as in real life, batteries have internal resistance, which is not present in the ideal model. So in conclusion, we predicted the behavior of circuits containing resistors in series and parallel, used multimeters to measure the actual values of conventional current and potential differences in the circuit, examine the behavior of ohmic resistors and capacitors, and overall, real-life circuits have noticeable differences when compared to ideal that we all should look out for when conducting experiments. Thank you.